So, so this is a particularly important result. So given any code, there's a connection between the minimum distance of the code and the number of errors and erasures it can correct. So if d min is or d is the minimum distance of the code, then it can, if d is odd, then the code can correct d minus 1 by 2 errors. If d is even, then it can correct d by 2 minus 1 errors. And it can always detect d minus 1 errors, and it can correct d minus 1 erasures. So for at least for these two classes of channels, for these three problems, one is error detection, one is error correction, and the other is erasure correction. So for these three problems, all we have to do is look for codes with large minimum distance. So if we can construct codes with large minimum distance, then we can solve these three problems, codes for these three kinds of scenarios, right? So now, so all of this is fine. Right now, there were some things that I had sort of overlooked. Right? We didn't really care about what the input alphabet was. We didn't care what the output alphabet. We kind of assumed that the input alphabet is the same as the output alphabet, but no further assumptions were made on the alphabet itself. It could be anything, any arbitrary finite set. Right? But now we'll start imposing some structure on the alphabet. Right? Because after all, we saw that linear codes were good. So if the encoding can be done as a linear transformation, then that's very efficient to implement. Otherwise, if there is absolutely no structure, then all you could do, you'll have to maintain some kind of a table or look for more complicated functions for encoding and decoding. So, but in order to even have linear operations, the alphabet can't be arbitrary. You need some kind of an alphabet over which you can do arithmetic operations. And specifically, the structure that we will look for is basically a field. Okay. So let's quickly recall what a field is. So a field is basically a non-empty set. I'll denote this by this script f, and the addition, and it has two operations. One is addition and the other is multiplication. So I'll denote addition in the field by this plus and multiplication by a dot. So these two are binary operations. It takes both of these take field elements, two field elements, and output another field element. So what property should it satisfy? Firstly, it should be closed. So basically, if I take any a comma b in the field, then both a plus b should be a valid field element, and a into b should be a valid field element. That's basic. And then we also want commutativity. So whether I do multiplication or addition, a plus b or b plus a, I should get the same result. So a plus b should be equal to b plus a, and a times b should be equal to b times a. And again, on similar lines, we want associativity. So the order in which you add or multiply should not matter. So I can first add b plus c and then add a to it, or this should be the same as taking a plus b and then adding c. Similarly, multiplication should also be associative. So the order in which you add or the order in which you multiply should not really matter. And in addition, there should be an identity element. There should be an additive identity and a multiplicative identity. So I'll call the additive identity 0 and the multiplicative identity 1. So the additive identity is such that A plus 0 equal to A for all field elements A, and A into 1 is equal to A for all field elements. So there exists two identity elements, so two special elements in the field, which we call the additive identity and the multiplicative identity. Similarly, for every element there exists an inverse. So we'll denote this, maybe I'll call it A bar. So addition of the element with the additive identity should give me, sorry, the additive inverse should give me the additive identity. And for all non-zero elements, there exists a multiplicative identity such that A times A inverse should be equal to. And one other property that we'll require is, so now we've individually looked at properties of addition and multiplication. So we also want these to interact in a nice way. So A times B plus C should be equal to A times B plus A times C. So as long as I have a set, a non-empty set with these two operations which satisfy all of these properties, this is what is called a field. And as we see, real numbers satisfy all of these properties. So we're trying to come up with the minimum set of rules on which we can perform all arithmetic operations just like we did in the real field. We don't need any extra operations. As long as these operations are there, then we can do a lot of other things. Okay, so now let's look at some examples. Which of the following are fields? So a set of real numbers with standard real addition and standard multiplication. This is a field. Right? It satisfies all of these properties. You're all convinced? Okay. So now let's look at some other sets. What about the set of rational numbers? The field? Does everyone agree? Agreed? What about the set of integers? Why? What? Okay, so can you give me an element which does not have a multiplicative inverse? So C does not. Not all. So the multiplicative inverse does not exist for all non-zero elements. So now what about the set of irrational numbers? So throughout I'll use the same notation. So R, this special R will be the set of real numbers, Q will be the set of rational numbers, Z will be the set of integers. So R minus Q is the set of all irrational numbers. Is this a field? Why? Why is it not? So what property is not being satisfied? So it's not closed under multiplication. What about the set of complex numbers? The field? Okay, so now let's look at some more interesting example. So I'll denote ZQ as the set of all integers modulo Q. So for any Q which is an integer, ZQ basically the set 0, 1, 2 up to Q minus 1. So it is 0, 1, 2, 3 up to Q minus 1. And addition and multiplication is modulo Q. So A B is basically A plus B mod Q. So the remainder, so you do standard integer addition of A and B, and then take the remainder when you divide by Q. And multiplication is just multiplication modulo Q. Okay. So just as an example, let us take Z2. Let us try to find out the table of addition and multiplication. So can you fill this table? So this is the addition table and this is the multiplication table. Yeah, 0. Okay, 1 plus 1 mod 2, so it is 2 mod 2, which is 0. What about multiplication? 0. So what are these operations? It's just XOR and AND. So addition modulo 2 is basically the same as XOR, and multiplication modulo 2 is basically the AND operation. Okay, so let's just take one other example, which is maybe Z3. What is the addition table? Zero, 1, 2, 0. Okay, and multiplication table. So 0, 0, 1, 2. 0. All right, so now we know what exactly what we're talking about. Now, is this a field for any general Q? So let's look at Z2. Is Z2 a field? So maybe let us look at each property one by one. So this addition modulo q and multiplication modulo q. For any arbitrary q, is it closed? It is always closed, right? Because you are doing modulo q, you will always get some number between 0 and q minus 1. So it is closed. Is it always commutative? Yeah, because it's the standard addition modulo q and standard multiplication modulo q. So it is commutative. Is it associative? For every q, it is always commutative. It is associative. What else? So does there always exist an identity? Additive and multiplicative identity? So 0, no matter what q is, 0 is always the additive identity and 1 is always a multiplicative identity. Okay. So is it distributive? It's always distributive. You can formally show this, convince yourself trying to this distributive. So it's distributive for every q. What about inverse? Additive inverse, does it always exist? A minus 1 won't exist, but so in this case, okay, minus 2, but is it, but minus 2 is not really in the set, right? That is why you have to think about it more carefully. What exactly does it mean to be an additive inverse? So you look at this particular table, right? So what is an additive inverse? You add something to each number, you should get a 0. Right? You know that 0 is the additive identity. So for every number, there should be an additive inverse, which means that for every number, there should be some other number, just that if you add the two, you should get a 0. So the additive inverse of 1 is 2 because it gives you a 0. The additive inverse of 2 is 1, so that's a sanity check. Right? Now, what about multiplicative inverse? You have to multiply, you have to get 1. Right? So does that exist? Yeah, for every non-zero element, right? So the 0 never has a multiplicative inverse. So, so both 1 and 2 are the multiplicative inverses of themselves in this particular case, in Z3. Right? So that is why don't get too attached to the 0, 1 and 2. I could have just defined something like this. So alpha, beta, gamma. These are 3 elements. And I can specify an addition table and a multiplication table. And you should still be able to check whether this forms a field or not. Right? So maybe let me rewrite something. Say that I give So suppose I give you this particular table. I have three elements. I call them alpha, beta, gamma, and I've completely specified how addition works and how multiplication works. We have to check whether this is a field or not. So let's look at addition first. Okay, so let's look at each property. I'm assuming that if there's more than two, okay. So first it is closed, right? Because all the entries are within the same set, alpha, beta, and gamma. Now, for this to be commutative, what should this array look like? Sorry, it should be symmetric, right? As long as the array is symmetric, the operation is commutative. And in this case, they are symmetric. Both are symmetric. So that is fine. Now associativity. You can also check whether this is associative or not. Basically, you take all combinations of three elements. So basically, you take alpha times alpha plus beta plus gamma. So you add alpha plus beta and then add that to alpha plus gamma, and you should get the same irrespective of which order you do it in. Okay. Now let's look at identity, because identities and inverses. So in this case, how would you find out whether something is an identity or not? What should happen? Okay, so I mean, visually speaking, how would you check? Beta is n. So basically, this should be repeated in the same order. So whenever I see alpha, beta, gamma, if there is a column containing alpha, beta, gamma, and a row containing alpha, beta, gamma in that particular order, then it means that that particular element is the additive identity. So one guess would be that beta is the additive identity. Correct? So now what about the inverse? Beta is additive identity, right? So now for each element, I need to find an inverse. Right? So what is the inverse of alpha? How do you find out? Gamma, right? Because alpha plus gamma is giving me beta, and the gamma plus alpha is giving me. So the inverse of the additive inverse of alpha is beta. Alpha bar is equal to gamma. What is the additive inverse of gamma? So that is fine. So now every element has an inverse, and every element has, and there's an additive identity. So this part is fine. Now what about multiplication? What do you think should be the multiplicative identity? So this alpha, beta, gamma appears in the same order in the first row and the first column. So you would guess that alpha is the multiplicative identity. So now what about multiplicative inverse? So beta is the multiplicative, is the additive identity, right? So we don't, so beta is never going to have a multiplicative inverse. So you need to check for the multiplicative inverses of alpha and gamma. Gamma inverse is gamma, because gamma times gamma is equal to alpha. alpha is the multiplicative identity. So gamma is the multiplicative inverse of itself. So beta is what? It is the additive identity, right? So it's basically our 0. And 0 never has a multiplicative inverse, because 0 times anything should give you 0. And that is why the row corresponding to beta and the column corresponding to beta are all betas. So basically you want to find the inverse of every element, right? Our guess is that alpha is the multiplicative identity. So you want to, so for every non-zero element, that is for every element which is not beta, you want to find the multiplicative inverse. So you look at the row corresponding to alpha, find out which element makes it equal to alpha. So multiplying alpha with alpha gives you alpha. So the multiplicative inverse of alpha is itself. And that always happens, right? Because it's a multiplicative identity. Now, beta we don't care. Gamma, we want to find the multiplicative inverse of gamma. So find out multiplying this with which element gives me alpha. In this case, it is gamma. So gamma inverse is equal to gamma. Alpha what? Alpha, yeah, gamma is the multiplicative inverse of itself, right? So gamma is the multiplicative inverse of gamma, not the multiplicative inverse of alpha. There is one unique multiplicative identity and there is a unique additive identity, but for every element there has to be an inverse. So basically this whole thing alpha, beta, gamma is essentially a remapping of 0, 1, 2. It's actually Z3 hidden. But what is important is that only the structure matters. How you label it doesn't really matter. I could call this apple, orange, watermelon. Doesn't matter. As long as I specify an addition and a multiplicative operation, which is consistent with all the properties of a field, it forms a field. So now let us go back to our problem. So I have ZQ, the set of integers modulo q with modulo q addition and modulo q multiplication. Yeah. Correct. So basically, given this table, you should verify that all operations are being satisfied. And some of them can be sort of seen visually, right? So for example, if multiplicative, if an inverse exists, then the additive element, the additive identity should appear once in every row and once in every column. Right? The same happens over here. And there should be an additive identity, there should be an identity element, which means that this particular column should appear at least once, and this particular row should appear at least once in the table. Okay. So now we have ZQ for general Q. What do you think should be the additive inverse of a particular element? So take any element A. So basically A is between 0 and Q minus 1. Now for the additive inverse, A bar should be equal to 0 because 0 is the additive identity, right? So now for A, what do you think A bar should be? Can you guess? Same? No. No, Q is general, right? So for example, if I take Q equal to 3, right? So 1 plus 1 is equal to 2 and 2 plus 2 is equal to 1. So it's not equal to 0. So when is the addition? So I have A plus A. Maybe I'll denote this special plus. So when is this equal to 0? So this is addition within, this is modulo Q addition, right? What can I say about the integer addition of A plus A bar? So basically I'm saying that A plus A bar mod Q is equal to 0, right? This is a restatement of this. Yeah, correct. So it is Q times some M for some integer M. Right? Okay, so now can you guess? So what can M be? What values can M take? Can it be any integer? If I take any two elements from 0 to Q minus 1, what is the largest the sum can be equal to? It can be larger, right? No, no, no. So I'm not talking about the modulo Q addition, just integer addition. I take two integers between 0 and Q minus 1. I add them up. What is the largest it can be? 2 times Q minus 1, right? So if A plus A bar is some integer multiple of Q, and both of these are A and A bar are positive integers between 0 and, sorry, non-negative integers between 0 and Q minus 1, have A plus A bar should be, so you said that this is less than or equal to 2 times Q minus 1, right? And this is obviously greater than or equal to 0, right? So if this has to happen, then M must be either 0 or 1, right? Because it can't be any less than 0, and it can't be even 2, right? Because 2Q is greater than 2 times Q minus 1. So this can only happen if uh, M is equal to 1, in fact. So what can you say about A bar? Q minus A. So if I take A bar to be equal to Q minus A, is A bar always an element in ZQ for every A? It is, right? Because A is between 0 and Q minus 1. A bar will also be between 0 and Q minus 1 as long as A is greater than 0. So for any A between 1 and Q minus 1, Q minus A is between 1 and Q minus 1. That's a valid field element. What about A plus A bar mod Q? It will be 0. A plus A bar mod Q is going to be 0. So this basically the additive identity. And this holds for every Q. No matter what positive integer Q you take, this is always an additive inverse for A. This for all Q. Okay. So what about multiplicative inverse? Does it always exist? Yeah. So you have A times A inverse should be equal to minus words A in Q be equal to 1. Now what can you say? What more can you say about it? What n Q plus 1? So A inverse, you can say that this is M times Q plus 1. Okay. Now can this always happen? So what do you want? What do you want to guarantee? That there is some integer M. So it can't. So what values can M take? Okay. So let me put it in a slightly different way. Uh, so all of these are integers, correct? So Q is an integer, M is an integer, A and A inverse should also be integer. So an inverse can exist only if you can find an integer A inverse and an integer M such that A inverse equal to MQ plus 1. Of course, this can't be any arbitrary integer. It should specifically be some integer between 1 and Q minus 1. Okay. So what more can you say about this? So let me write it in another way. So you want MQ to be equal to AA inverse Okay, so let me not the right way to put it. Now, suppose that so let us take some example. Okay, let us take Q equal to 4. Okay, Q is equal to 4, and let me take A equal to 2. So I'm taking Z4, and within that I want to know if 2 has an inverse or multiplicative inverse or not. So basically I want to find 2 into A inverse should be equal to M into 4 plus 1. Correct? So I want to find some integer A inverse and some integer M such that this happens. Can I find some A inverse and some M? So I know that A inverse can only take one of 4 different values, right? 0, 1, 2, 3. Yeah, so I want some, so if I can satisfy this particular equation using some integer M, then I'm fine. Correct. So the left hand side, no matter what I take, the left hand side is always an even number, whereas the right hand side is always an odd number. So this can never be satisfied. So what does this mean? What can you say about Z4? Correct. So Z4 is not a field. Okay, so now we've seen that there are some values of Q for which ZQ is not a field. What do you mean except 2? Yeah, for Q equal to 2, agreed, it is a field. For 4, it is not a field. Now, can you extend this 6 y? Correct. So 2 will not have an inverse, right? Okay, so now can you generalize this? So we know that Z3 is a field, correct? We checked it using that particular table. Sorry, what? Okay, so you're claiming that for all odd Q, it is a field. Okay, so now let us take Q equal to let's say 15. Take Q equal to 15. It's an odd number, right? Try to find, say, take A equal to 3. P A inverse should be equal to M into 15 plus 1. Now I just want one counter example, right? So if I want to show that something is a field, I have to show that every element should have an inverse. Can you use the same argument? So 2 A inverse should be equal to M into 15 plus 1. Okay. Now I can take, say, M equal to 1. So the right hand side will be 16. I can take A inverse equal to 8. So I can find an inverse for 2. I'm choosing this 3 for a specific reason. Yep. Why can this not be satisfied? Uh, okay, it won't be an integer. Okay, can you sort of, okay, so yeah, you're getting at it. Oh, you want an integer. You want an integer. So the left hand side, what can you say? This is divisible by 3, right? The right hand side is never divisible by 3. Okay, so now can you guess? So any guesses as to why I chose 15 and 3? So 15, so 3 is, so 15 is a multiple of 3. So if it, suppose that Q is composite, okay, suppose it's composite. So then basically you can write Q as some whatever alpha times beta, right? Now if you take alpha times alpha inverse to be equal to m times q plus 1, if you look at this particular equation, the left hand side is a multiple of alpha, but the right hand side is m times alpha times beta plus 1. So the right hand side can never be a multiple of alpha. Alpha cannot divide the right hand side, but alpha will divide the left hand side. So does not have an inverse. Now what you want to show, so this is if Q is composite. So if Q is composite, then ZQ this is not field. I'll just leave it as a homework. So you have to show that if Q is prime, then ZQ is always a field. Basically, the only property that you need to check is that every element has a multiplicative inverse. You can prove that particular property, then you're done. Maybe by the next class, you can try to prove that ZQ is a field, prime Q. Now let's look at some other examples. So let us look at the set of all possible polynomials over with coefficients coming from some field. I'm trying to see if it is possible to create a bigger field from a smaller field. So the set of all polynomials. So let's take the set of all polynomials with real coefficients. Okay, and why do you say that? Not a field. Why is it not a field? So typically, whenever you are faced with such a problem, the first thing that you should try to check is if every element has an inverse. More often than not, that is the one property which is violated. Does every element have a multiplicative inverse? What about X? Does X have a multiplicative inverse? Can I multiply X with some other polynomial? It equals 1? Not possible, right? Because if I multiply X with any polynomial, the degree of this polynomial will be at least 1. It has to be at least 1. And so this is not possible. So not a field. In some cases, it is possible to construct a field, but using a different multiplication operation. So let me look at the set of all polynomials. So the following set of polynomials: 0, 1, 1x, and 1 plus x. So this is polynomials over the binary field. So I have 4 elements, okay, and addition is modulo 2. So basically 0 plus x is x, 1 plus x is x. So this is the addition operation, but I'm going to define multiplication in kind of a funny way. Zero is one is the multiplicative identity, but now so this is my multiplication table. You can verify that this in fact forms a field. So does every element have a multiplicative inverse? What is the multiplicative inverse of x? Plus x. Multiplicative inverse of 1 plus x is we can go through all the properties and you'll see that this satisfies all the properties. We'll see that later in the course. So I've sort of wrote this table very quickly because I knew how to construct this particular field. So here's a sort of hint. We'll see how to construct such fields, but sort of a peek into how I constructed this particular field. It is basically kind of like we did with the integers. So I took the set of integers modulo q. When q is prime, I know that the set of integers modulo q with modulo q addition and multiplication, that forms a field. Now it turns out you can generalize this to polynomials as well. So you look at the set of all polynomials modulo some other polynomial. If I choose the polynomial carefully enough, then it turns out that this forms a field. So in this case, it is 0, 1, 1 plus x, x. And the addition and multiplication are actually modulo 1 plus x. But this is over the binary field. The coefficients are coming from the binary field. So we'll go into this in more detail later on in the course. See how to construct fields, how to do addition and multiplication operation over more complicated finite fields. Right? But this is basically how I constructed this particular field. It turns out that this polynomial over here is special. Now if I instead took mod 1 plus x square, it turns out that this does not form a field. Because there's a similar idea, prime and composite number. So we'll see polynomials which are kind of like primes and polynomials which are like composites. Okay, so another example. What about the set of all n by n matrices? Why? Okay, so commutativity is not satisfied, so it's not a field. So multiplicative inverse does not necessarily exist. Associated, it is associated. Okay, so here's something a little more interesting. So the set of all matrices which have this specific structure, set of all 2 by 2 matrices of the form x minus y, y, x, where x and y are real numbers. Why? What do you mean single matrix? Correct. No, B will be what? So A will be x1 minus y1, y1 x1, and B could be x2 minus y2, y2 x2. Right? So you have to verify that if I multiply two such matrices, firstly it follows this specific form. I should be able to show that the product is equal to some x3 minus y3 minus y3 x3. Okay. You have to check. Associativity is not really hard because after all you're doing matrix multiplication, so matrix multiplication is in general associative. But everything else from commutativity to identity, inverse, even closure, you have to verify. Because I could multiply these two and I could get something which is not of the form x3 minus y3 y3. It could be some x3 minus y3 z3. Is it closed? I multiply 1 minus y1 1 with x2 y2 2. What do I get? x1 2 of okay. What is the identity element? What is the additive identity? All zeros. So this is of this form. What about the multiplicative identity? Identity basically you take x1 x equal to 1 and y equal to 0. Correct. What about the inverse? Okay, what is it? Uh, Inverse is so is this a field? It's a field. Do you notice any special structure? Is it a familiar structure in some way? Okay, kind of close, but I mean, but then cos theta, sin theta are always between 0 and 1. Here x and y can be arbitrary real numbers. Sorry, they're between -1 and, but here is anything special? So let's look at the addition operation. Basically, what are you doing? You're taking some xy pair, some x1 y1 pair plus x2 y2 pair. Effectively, that's one way to represent it, right? You can represent each of this using just a pair x and y. right? So taking an xy pair, I'm adding another xy pair, I get x1 plus x2, y1 plus y2, correct? Well, this is just real addition. Now what about multiplication? What happens? What do I get? Yeah? What do you mean one element is two? X1, x2? So it basically corresponds to this element, right? This is my x, correct? And this is my y, right? So I multiply x1 y1 with x2 y2. I'll get minus y1 y2, correct? So this is basically another way of representing this matrix. So instead of, I can write whatever x1 minus y1, y1 1. I can sort of compactly write this as x1 comma y1. Implicitly there's some operation, there's some structure over here, but there are only two free variables, right? X1 and y1, and I can just write it as x1 comma y1. That's exactly what I'm doing here. So I take these two matrices and add them up. Basically it's like adding these two pairs to get this particular pair. If I multiply these two pairs, then I get this particular pair, correct? All fine so far. Now is this something that is familiar? I have a pair x1 y1. Addition is just, yeah, whatever, component wise addition. But now I'm multiplying x1 y1 with x2 y2. I'm getting x1 x2 minus y1 y2 and x1 y2 plus y1 x2. You've seen this in exactly complex number. It's basically another representation of complex number. I could as well write this as x1 plus iy1 and x2 plus I. Get the same. So whether you represent it using this or you represent this using in this particular fashion, or you represent it as x plus iy, they're basically all the same. So algebraically, they all represent the same set of operations. This with standard matrix addition, multiplication, this is exactly the same as operating over complex number. This is another representation of complex number. So we say that this is isomorphic to the field of complex number. Two fields which are essentially isomorphic. Yep. Choose one. Exactly. So maybe in one operation you can kind of implement multiplications more easily in one particular representation. Then you use that particular representation. Okay, so I leave this one more thing as an exercise. So x plus y root 2, where x and y are rational numbers. X and y are rational numbers. Set of all pairs which are the form x plus y, all set of all numbers of the form x plus 2 for x and y being rational numbers. Find out whether this is a field or not. If it is a field, then basically check that all the properties go. Okay, so right now, so now we have a set over which you can do additions and multiplication. And now we want to construct linear codes over these particular sets. So for this, we need the concept of a vector space. So what is a vector space? So we say that a vector space over some particular field. So we have an underlying field, and on this you construct a vector space. So a vector space is some set, again non-empty set with operations plus and multiplication. Say that this forms a vector space over some particular field if again a bunch of properties are satisfied. So firstly you have commutativity of addition v1 plus v2 is equal to 1 for v1 v2 in the vector space. So remember that this addition is addition of two vectors, whereas multiplication is multiplication of a field element with a vector. Right? So the elements of the vector space are going to be called vectors, and they'll sometimes use an underline to denote that this is a vector. It's just to make it convenient to distinguish between field elements, scalar elements, and vector elements. And then you have associativity, is v1 plus v2 plus 3. Again, it doesn't matter in which order I add these. And there exists an identity element. So there exists a zero vector in the vector space such that 0 plus vector is equal to itself. And there always exists an additive inverse v bar zero vector. And again, multiplication is kind of compatible. A times some vector, where A is a scalar, A is coming from the field. If I have V times A times V, it's the same as V times A times V. Exactly. This is the first property right now where we're picking elements from the field. So basically, all of these things are compatible and also equal to A times V times V. And the multiplicative identity has the, so if 1 is the multiplicative identity, it's a field element, then 1 times V is equal to V. And again, not a property, but a consequence is that the zero element of the field times any vector will always give you a 0. And one way to see why this is the case is because so you want 0 plus any alpha v to be equal to alpha times v, because 0 plus alpha is alpha. But then this is 0 times v plus alpha v. These two get cancelled, so 0 times v should be equal to the 0. So now you also want some distributivity properties. Hold. So if you add two field elements and multiply it with a vector, then it should be the same as doing a times v plus b times v. Similarly, if I multiply it with a sum of vectors, it will be equal to a times 1 plus a times. Basically, you have these set of properties. Something we know what real vectors satisfy over the real field satisfy. Therefore, this forms vector space. I assume that you've all taken a course on matrices, or so this should be familiar. Now, let's look at some examples of vector space. Can you give me some examples? Okay, so set of all polynomials is forms a vector space. What about the set of all polynomials of degree less than or equal to some particular number, say less than or equal to 10? Does this form a vector space? Agreed? Okay. Everyone convinced? Less than or equal to integer k if you want. Okay, so some more simpler vector space. Rn over R over C. In general, take any field Fn over F is a vector space. What about F over F? Why? What about R over R? What about R2? R2 even R2 has uncountably many elements, right? If just take n equal to 1, so every field is a vector space over itself. Okay, so these are fine. What about, say, the set of all differentiable functions on R? Vector space. So in particular, the sum of differentiable functions is another differentiable function. Any linear combination of differentiable functions is also differentiable. Here's a slightly more complicated thing. What about R over Q? Q is a field. R is also a field. What about R over Q? The field is Q and the vector space is R, or whatever. The set is R. Set V is equal to R. Does this form a vector space? It does. What is the dimension of this vector space? what is going to, okay, Q is, and R is uncountably in. So what should the dimension be? So R is you're saying that R is a vector space over Q, right? So every vector space has a dimension, right? So dimension is the size of the smallest size of the basis. Okay, correct. So it's a vector space, true. But what do you think the dimension should be? Any guesses? Do you think it is finite dimensional? So take any two irrational numbers, say root 2 and root 3. Are these two linearly independent or are they linearly dependent? Hmm? But is that a rational? Remember, the field is Q, right? So if root 2 and root 3 are uh, linearly dependent, then you should be able to write root 2 equal to alpha times root 3 for some rational alpha. Is that possible? Root 2 and root 3 are linearly independent. So you take any two irrational numbers, like most irrational numbers, these are going to be linearly independent. So now, what do you think the dimension is? Do you think this is a finite dimensional vector space? It's an infinite dimensional vector. And particularly, you can take irrational numbers, you can take transcendental numbers. All of these are going to be linearly independent. E and root 2 are linearly independent. Phi and root 2 are linearly independent. This is an example of an infinite dimensional vector. Okay, so let's stop here.